Marhaba. Okay, in this video, we want to add a new strategy to our arsenal of proof techniques. So recall previously we learned how to prove universal statements and how to prove a conditional statement of the form P implies Q via a direct proof. So remember, so we have a conditional statement. Say P implies Q, and the direct proof strategy says that assume the hypothesis P is true, and then use the axioms, the previous theorems we proved, the rules of inference, and the hypothesis P to show that Q must also be true. If we do this, then we prove that the whole conditional statement is true. Sometimes when we assume P to be true and try to show Q is true, we are stuck. We reach a dead end. And at this point, we need to rethink our strategy. So another strategy to prove a conditional statement to be true is called proof by contraposition. So it relies on the following logical equivalence. So remember previously we showed that these two statements are logically equivalent. So logical equivalence. What was it? That a conditional statement P implies Q is logically equivalent. It has exactly, it always have the same truth value as its contrapositive. So not Q implies not P. So what is the strategy of proof by contraposition is to prove the contraposition is true. So prove this is true by a direct proof. Okay. So what is this? This is a conditional statement whose hypothesis is not Q and its conclusion is not P. So by a direct proof, we assume not Q to be true, and then we show that not P must be true. If we do this, this means that this conditional statement is a true statement. It's always true. But since this is logically equivalent to this, which means they have the same truth value, and we prove that the right-hand side always have a true value, this means that the left-hand side always have a true value, always has a true value. So this is how we prove P implies Q is true by contraposition. So let me sum up. Okay, so to prove P implies Q is true by contraposition, we do the following. First, we assume not Q to be true. So assume not Q is true. And then we do steps here, which uses the axioms, the rules of inference, previous theorems. And finally, we need to get to the conclusion of the contrapositive. So finally, show that not P is true. If we show this, this means that not Q, so not Q implies not P is true, right? If we assume not Q and show that not P must be true, this means that not Q implies not P is a true statement, but this is the contrapositive of our original conditional statement. So equivalently, they are logically equivalent. Equivalently, we have showed that P implies Q is true. So in short, to show a conditional statement is true, we show its contrapositive is true. And this is proof by contraposition. Let's take a quick example. Proof, so theorem, prove the following theorem. Let n be an integer. So this is a universal quantifier. Choose any integer n. And prove that if 3n plus 2 is odd, so if you multiply n by 3 and you add 2 and you get an odd number, an odd integer, then n itself is odd. Okay, so proof. Again, the first step we do before we start the proof is to understand the logical form of the statement that we want to prove. So here we have a universal quantifier, let n be an integer. So to take care of the universal quantifier, we choose an arbitrary element in the domain. And here the domain is the domain of integers. So choose any integer n. Now we need to show that the conditional statement is true about n. So what is the conditional statement? This is the hypothesis of the conditional statement, 3n plus 2 is odd. And this is the conclusion of it, n is odd. Now I'll let you try to prove it by a direct proof. Assume the hypothesis show the conclusion. But now we want, maybe you will be stuck, but in this example, we want to prove it by contraposition. So we need to show the contrapositive is true. So let's see, let's call this hypothesis P and the conclusion Q. And so we need to show that not Q implies not P. So we assume not Q. Now, so suppose not Q, suppose n is not odd, but not odd means even. So suppose n is even, and now we need to show not P. So our goal is to show 3n plus 2 is not odd, it is even. Okay? Let's try to do this. Suppose n is even, then what does it mean to be even? By definition of even, there is an integer k such that n is equal to twice k. Okay, so we know this by assuming not q, by assuming n is even. Now we need to show not p, which means 3n plus 2 is not odd, it is even. So now let's see what's now 3n plus 2 is equal to 3 times n, but n is 2k plus 2, and this can be written by associativity and commutativity of multiplication as 2 times 3k plus 2. Now we can take 2 as a common factor, and we will be left with 3k plus 1. Okay, but since k is an integer, then 3k plus 1 is an integer. Let's call it m. So this will be equal to 2 times m. Okay, since 3n plus 2 is twice an integer, this means that 3n plus 2 is even by definition of even. Is even. So now what did we show? We assumed, let me say it here. So we assumed that n is even, but notice that n is even is not q, right? This is not q. And then we concluded that 3n plus 2 is even, but 3n plus 2 is even is not p. Okay, so this is not p. So we showed the contrapositive. We can, this proves the contrapositive. The contrapositive of what? The contrapositive of the statement in the theory that if 3n plus 2 is odd, then n is odd. Its contrapositive says if n is not odd, then 3n plus 2 is not odd. In other words, If n is even, then 3n plus 2 is even. This completes the proof, and we finish it by a black square here. So we don't need to say that a contrapositive is logically equivalent to the conditional statement. We know this. Remember, in mathematical proof, we avoid we skip many justifications just to make it easily read. So now we should know that if we prove the contrapositive to be true, this means that the conditional statement itself must be true. And this is what we did here. Instead of proving P implies Q, we proved not Q implying not P. We assumed here is not Q, we assumed not Q to be true, and we proved not P to be true. So this means we proved that not Q implies not P. But we know this is logically equivalent to P implies Q. Since we proved this is to be true, then we proved that P implies Q is true. And this shows the general strategy of the new strategy of today, which is proof by contraposition. In summary, to prove a conditional statement by proof by contraposition, you prove it's contrapositive. So to prove P implies Q is true, we prove that not Q implies not P to be true by a direct proof. So we assume not Q, and then we show not P to be true.